Good afternoon, everyone. Today, we have one of our professors from Department of Applied Chemistry, DTU, Dr. Deenan Santhiya ma'am. Her research focuses on gene delivery applications, environmental biotechnology, nanobiotechnology, and surface chemistry. She has previously been research assistant at IGIB Delhi and research fellow at Max Planck Institute for Metal Forschung, Stuttgart, Germany, and National University of Singapore. I welcome Deenan Santhiya ma'am.
Thank
Over
you,
to you,
Vidushi.
ma'am.
Thank you, Vidushi. I'm sharing my screen now. Okay. Can you see my screen? Hello?
Ma'am, present your screen. You may now present your screen.
Okay, 1 minute. Yeah, share screen. Okay. Yeah. Can you see my screen?
Yes, ma'am.
Okay. So I'm opening my slide. Yeah. So good afternoon all. I'm Dr. Deenan Santhiya from Applied Chemistry Department. Today my topic is template-assisted calcium-based drug carriers for efficient oral delivery application. This is my topic. I'm going to concentrate on oral delivery drugs. First, as an introduction, what is an important of calcium? I would like to speak on calcium-based drugs and which are porous, sense high drug loading capacity, and it has a in vivo stability and naturally present in human body, pH dependent solubility, and EC surface modification. So biocompatible and biodegradable. That's why I'm interested uh, to focus on calcium-based drug carriers. Okay. So, since my route is a oral drug delivery route, and there are advantages on oral drug delivery. This is patient acceptability and compliance, large surface area, prolonged retention, and commercial advantages. Coming to the disadvantages, the patient variability, extreme pH is also there, is acidic pH, and intestinal motility and mucus barrier. These are all the difficulties. Whatever the carrier we are designing, it should overcome all these difficulties. Okay, so again, through the oral route, the drug has to reach the target area, the colon. Okay, the why I have chosen the colon as a target. It's a longer residence time. Okay, due to the longer residence time, less enzyme activity, and natural absorptive characteristics, but it needs a suitable carrier. We need a suitable carrier to process. So, so based on this, we have designed research gap found in the literature, the calcium carbonate nanoparticles. Okay, and since it's a calcium based drug carrier, we are designing the calcium carbonate is also as a calcium ion also. Two aspects I am going to see. The calcium carbonate nanoparticles in the size range. We would like to have size range around 10 nanometer, which is very difficult to make it because the calcium carbonate synthesis is very fast and the particles grow bigger in size. Our aim is to control the size also to 10 to 15 nanometer. And the pectin, we have chosen another matrix for preparing this for synthesizing the calcium carbonate nanoparticles, that is pectin and PEG blend. Polyethylene glycol is a pectin PEG blend. Okay, the pectin is a natural molecule. It is a plant-derived macromolecule, and PEG is a synthetic polymer, FDA approved. Okay, so the work on pectin-based hydrogen is less in literature, okay, especially in the targeted delivery. Okay, that's why we are interested here. And coming to the major objectives, okay, what are the major objectives? To fabricate the target specific oral delivery vehicle for controlled co-delivery of nutrients. There are two difficulties, two barriers I have to cross. I have to reach the target. Also, the co-delivery is a focus. The delivery co-delivery means we are releasing the nutrients or drugs uh, uh, with accompanied with some other molecules. Okay, and control over the delivery is also the very important. To delineate the mechanisms involved in the fabrication of drug carriers, and understanding the in vitro swelling studies of drug carriers in stimulated gastric fluid as well as stimulated intestinal fluid of different pHs. You know that stomach pH varies from around pH 1 to pH 7. So we have to design the in vitro experiment. These are all the targets. Okay, first aspect what I'm going to speak is on pectin PEG food grade hydrogen blend targeted co-delivery of nutrients. I'm going to concentrate on the nutrient delivery. Okay, so coming to the pectin PEG food grade hydrogel blend for targeted oral delivery. Okay, in this, see, we are going to concentrate calcium 2 plus. We are going to co-deliver with vitamin D and iron ions with vitamin C. Okay, these two be entrapped in pectin PEG hydrogel matrix, and these two nutrients are we are going to study the in vitro release in SGF, simulated gastric fluid, and simulated intestinal fluid. So co-delivery is important here to enhance therapeutic efficiency of controlled delivery with synergic activity. Okay, this is very important. For example, the vitamin D is for healthy bone and teeth. And vitamin C is useful for growth and repair mechanism. So there's a thing. And pectin, coming to the pectin, why I have chosen pectin? Pectin is a biodegradable and biocompatible material. It's an edible polysaccharide, and it, more importantly, it has a good gelling property. It reduces the cholesterol, serum glucose, and also has anti-cancer activity. Okay, and most important property is mucoadhesive property. And again, PEG is a small, it is around 300 molecular weight. Okay, around 300 of PEG is used. Pectin is a macromolecule, and a PEG we used here as a cross-link. It is a cross-linker. See, any hydrogel we need a cross-linker. Then only we can make the hydrogel possible to make the hydrogel. So it's a water-soluble polymer, biocompatible, non-toxic, and FDA approved. And biomedical application, and mucoadhesive property, also mucoadhesive properties. For this part, the objective is to fabricate and we are characterize pectin PEG hydrogel blend and entrapping the nutrients and understand the release mechanism. Okay, co-release mechanism. This. Okay, so the how we made the sample, it is a very simple mixing. We have taken the pectin solution, 30% is pectin solution. We added citric acid to control the pH from 3 to 3.8. So this pectin solution, we added PEG. So first hydrogel, blank hydrogel is ready. The another hydrogel, we made pectin PEG along in the mixture. We added calcium chloride salt and vitamin D. So another hydrogel is ready. Third hydrogel with iron and vitamin C. So 3 different hydrogels are ready. The blank is named as PP, pectin PEG, and next one is pectin PEG, the calcium with vitamin D, and pectin PEG, iron, vitamin C. So we made all these hydrogels by simple mixing using a test tube, which is of 25 ml capacity and 1.5 centimeter diameter. Okay, this is the hydrogel length, whatever we made it. Length of the hydrogel around 10 centimeter, and is around 1 centimeter in dia and 1 centimeter in thickness. Okay, so coming to the characterization, and first FTIR characterization has been done. FTIR characterization, if you see that pectin PEG hydrogel, this region, if you note this region carefully, this region is mainly for the OH group, and which is present in the pectin, and carbonyl C double bond O group, and carboxyl group COO minus group. Okay. So when this in the presence of the calcium and the vitamin D, what is happening in this region? The bond is enhanced. Okay, this you see that intensity of this. Okay, that means the calcium 2 plus. It shows the interaction of the calcium 2 plus ions with this region. That interaction is mainly due to the electrostatic. Here again, you see the enhancement. Okay, this is a good point for our sample is made. That means we electrostatically we made the this nutrients. We interacted the nutrients with the pectin PEG matrix. Okay, coming to the TGA studies, thermogravimetric analysis. Here, if you see that pure pectin PEG, there is no remaining at all, no residue at all at 400 to 500 degrees centigrade. Whereas with PPCAD and PPFEC, these two hydrogels, you could see that some remaining is there here. Okay, the residue is there. This residue shows that there is a presence of metal ions. Metal ions we cannot thermally degrade. Okay, that means our experiment is successful. And SEM images shows the porosity on the hydrogel. Of course, naturally hydrogels are porous in nature. This is coming to the very important property, the rheology. Why we have to do the rheology? Because these two oral carriers are mucoadhesive. For mucoadhesiveness, we need a elastic nature. Okay, then only it will spread on to the organ. Okay, so the body will absorb. It will. So if you see this PPCAD, that means pectin PEG hydrogel containing calcium, vitamin D. The temperature, gelling temperature, that means when it makes a semi-solid, so gelling temperature takes place at 32 degrees centigrade. And the more importantly, like you see that loss modulus and G prime is a loss modulus, G double prime is a storage modulus. The increase in loss modulus is seen here. That shows that elastic property of the material increases. Okay, whereas viscosity property of the material decreases. Okay, this is the important finding. That means hydrogel formation has been taken place. Okay, here also the same. Okay, coming to the other properties with frequency variation, what we could find is we could find G prime. This is loss modulus. Loss modulus of this sample in the case of PPCAD is more. That means this is elastic property is more. Is elastic property of this PPFEC, that is iron containing sample, is less. As we know the chemistry, the calcium binding onto the pectin is weaker. The iron is a very strongly it binds. So it is very rigid material compared to calcium 2 plus. This is very important finding of the chemistry. And coming to the swelling and degradation, why the swelling is very important? So whatever the drug we take inside orally, it should interact with the body fluid. Okay, coming to the oral delivery, obviously the drug will interact with the stomach and then intestinal fluid and other things. we have designed the in vitro experiment. That means we have done the swelling of 1 centimeter thickness, 1 centimeter dia of that part of the hydrogel. We dipped into simulated gastric fluid at pH 1.2. Any drug we have to preserve in the stomach. Okay, this drug, our aim is to release in the colon, so we have to preserve the drug in the stomach. So the beauty of the pectin is when the at pH 1.2, the protons are more, so the protonation is possible at on the pectin. That means due to the H plus ion absorption on the pectin, what will happen? It doesn't allow the molecule will deswell. It doesn't allow the entry of simulated gastric fluid. That's why it doesn't, even the material, the drug has been put into the simulated gastric fluid, we didn't absorb much swelling here. There is no swelling. Okay, we can say that around feeble swelling. Okay, so after up to 3 hours. So that means your inside your nutrient that is Ca2 plus and Fe3 plus, Fe2 plus, both are retaining into the, and obviously along with the vitamins are retained in the drug carrier. Okay. So then when we increase the pH, so when we the pH is around intestinal pH around 6.8, and swelling is taking place here. Okay, so the matrix opens, the since the protons are not there, the protonation is not there, so swelling is happening freely, and you get good swelling here. And you can compare to the calcium containing sample as a more swelling, and compared to iron, that is the rigidity of the sample. This shows the flexibility of the sample. So degradation, coming to the degradation studies, we could the sample could degrade 80% or above at 9 hours. Okay, obviously after some time you can see the decrease in swelling. That shows the disintegration of the drug carrier. These are all interesting findings. Okay, so drug release study, this is actually coming to the drug release analysis. We can see that around so the drug is very selectively released at selective release at the colon. Okay, this is the thing. And so findings, important findings coming as a conclusion. As a conclusion, we can say that nutrients, calcium along with vitamin D, and we could release at the colon, and interesting oral delivery vehicles fabricated here is using the pharmaceutical approach, and could be easily incorporated into the ready to eat functional foods to promote health benefits and expected to overcome common human health problems. Now Vidushi, do you have extra time, or shall I stop with this?
No, ma'am.
I can continue?
As long, yes, ma'am.
Yes, thank you so much. So coming to the next part of my presentation, in situ mineralization of. So far, last part, I discussed about the calcium ions and how to release the nutrients and co-release the nutrients at the colon. Here, very important is important drug, protein release we are going to discuss. And in situ mineralization of calcium carbonate in pectin based edible hydrogel for the delivery of pectin at colon site. Okay, this is the topic, the next part topic. Here the main objectives are to mineralize calcium carbonate particles in pectin PEG based hydrogel blend. Okay, and understand the mechanism of mineralized calcium carbonate and characterize prepared hydrogel matrix through different techniques. To load and release of BSA as a model drug in SDF and SIF. Okay, so the same way here the mixing has been done. Okay, by simple mixing we made the hydrogel. Okay, three different hydrogel PP. This pectin PEG is a basic blank hydrogel, and next one is PPC, means it is calcium carbonate particles are introduced in situ in the hydrogel matrix. And next one is here we have chosen BSA, bovine serum albumin, as a model protein, and we are using next gel is pectin PEG and bovine serum albumin PPB as a gel. Last one, if you see that PPCB, that is calcium carbonate is also there, BSA is also there. This is the hydrogel we made. You can see the hydrogel. This is a sample, 1 centimeter thickness and 1 centimeter diameter. Okay, so FTIR characterization coming to the FTIR characterization, you can see PPB. If you see that here, this especially this region shows that a protein is present. This is amide 1, amide 2 bond, and this region, if you see that in the PPCB, the protein is also there, the carbonate also there. That means calcium carbonate and BSA is also there, and this is only the calcium carbonate is there in PPC. Okay, so then weight loss. The weight loss shows that similarly the weight loss is there. The existence of calcium carbonate particles shows this residue. Okay, XRD shows that the sample is amorphous in nature. Okay, so the elastic nature. The elastic nature of material is proved from this. We have this shows the elastic nature, and so coming to the SCM images, you can see carefully. You can see this PPC, the calcium carbonate particles. Okay, PPC here these are all plain surface, no particles at all. Here also no particles at all. This is only the pectin, PEG, and bovine serum albumin. This is pectin, PEG is a blank, and this is with the calcium carbonate and bovine serum albumin. This you can see the particles here, calcium carbonate particles. So coming to the TM images, we could find interesting observation. Of course, our PPC shows that this calcium carbonate particle, that is around 200 micrometer sized particles, and this is enlarged version. You can see only that. In the presence of BSA, we could see some coating around this particles. Okay, this shows the indication that something coated around this calcium carbonate particle. We are interpreting maybe this is due to the protein. Okay, that I will explain how it has happened. Okay, again the swelling studies. Here we are stopping the release of the swelling of the material due to the pectin. Pectin is protonation. Okay, on the other hand, in the intestine, it swelling, and it shows that releasing is possible, and colon. Okay, so you can see that the release BSA release here in the presence of calcium carbonate, it is intact. On the other hand, PPB, only wherever the BSA is there, the release is intestine itself, it is getting released. Okay, so here only release colon. Very important. Degradability of the material is also there, so it is suitable for oral delivery. So coming to the STS page, okay, so whatever the solution we got, so whatever the solution we got it, and we could see that we could run the gel. Okay, in the PPB, that is with the BSA, so it is releasing at 1.2, 6, 0.8. On the other hand, when calcium is there, it is released only at after 9 hours at colon. So the run shows that this is BSA alone, and you can see that this material is released all pH ranges, whereas here it is released only at the colon site. Hello. 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 Hello.
Yes, ma'am.
So connectivity is proper?
No, ma'am, we are
You
not able
could
to
hear.
see your screen.
Okay, now I have to project once again, come out and go again. I'll try again. Link is unstable.
In the meantime, if anyone has any questions, please feel free to ask them or
Yeah,
drop
that is better.
them in
Yes.
a chat box.
Yeah. Yes, please. Okay. Chat box. Yeah, chat box. Able to have it. Can you see now?
Yes, ma'am, your video is visible now.
But this screen is not visible.
Yes, ma'am, screen is not visible.
So better I will end the show and then I'll come back. Okay. Meeting. So can you see the screen now? Hello?
No, ma'am.
No.
Yes, I'll launch the meeting again. So I'll go back to my link and then again I will try. Okay.
Okay, ma'am.
But my is not visible. Okay.
Vidushi, in case
Yeah. Yeah, I am coming with the share screen. I can. Okay. Yeah. Can you see now?
Yes, ma'am.
Okay, fine. Okay. So here when I come to the slide, you can see the primary structure stability and secondary structure, tertiary structure also stable. Okay, so that means our protein sample is intact. Okay, intact in our carrier. This is the interaction of the molecules. This especially explains the interaction of the molecules. This is a pectin and this is PEG. It is interacting through the physical forces, that is through the hydrogen bonding. When we add the calcium carbonate, this is calcium carbonate interacts with the carboxyl group of the pectin molecule, and It is reacting with the carbonate and making the particles like this. And based on the surface charge, if you see that pectin PEG dono negatively charged, coming to the calcium carbonate, it is feebly negative. So the protein interaction preferentially goes to the feebly negative surface of this calcium carbonate. Okay, that's why we could see the protein part on the, we can visualize the protein part in the TM on the calcium carbonate particles. Okay, so as a concluding this one, I would like to conclude BSA loaded calcium carbonate particles are successfully mineralized. TM exhibited the accumulation of BSA was around mineralized calcium carbonate particles. In vitro protein release experiments were successfully demonstrated at the pollen site and were shown at to retain its conformational stability up to 9x. So I would like to significance of the present work. It provides the easiest route as a oral drug delivery. It's an eco-friendly synthesis, less time consuming, no need for high temperature furnaces, and cost effective. I thank my PhD student for this work, and also I thank the conference organizers and a convener, HOD of the Department of Biotech for giving me this great opportunity. Thank you all for giving me this great opportunity.
Thank you, ma'am, for sharing your research findings with all of us.
Yeah.
We have a question for you from
sure.
Apurva.
Yes.
From the studies, you conclude that both PPCAD and PPFEC both were giving good delivery, but which of them had more efficacy?
Efficacy, if in the sense the calcium is more efficient, PPCAD is more efficacy, because the iron, when you see that chemistry of iron, it is very strongly, it will bind onto the pectin. Okay, release is difficult. So the efficiency to release the calcium is more, calcium and vitamin D, of course.
Okay. Thank you, everyone. Now we will have a break till 2 p.m. and at 2 we will start with the student oral presentation. So all the participants of student oral presentation are requested to rejoin at 2 p.m. Thank you, everyone.